in the first in the fourth video of this course, I introduced to you the state of matter, and I talked about the different gas laws that govern the gaseous state of matter. So today we are going to delve deeper into that, and this topic for today's episode is molecular theory. Now, molecular theory talks about the fact that gas laws, Gleduzown's law, Dalton's law, Avogadro's laws, Graham's law of diffusion, and all the rest. So that is under molecular theory. And in addition to that, we'll be doing some calculations on molar volume of gases. We'll be doing some calculations on calculation of Avogadro's constant. Then we'll be doing some calculation on finding the composition and the molecular formula of a compound from its empirical formula. So sit tight and let's dig deep into this delicious meal of chemistry. Now, gas laws from the if you've not watched episode 4 of this series on state of matter, you can go and check it out. So I gave a foundation on gas laws, and then I'll be taking up this from there. So now, gas law, I talked about Boyle's law, which states that the volume of a gas is inversely proportional to its pressure. So in that case, V is equals to K over P. That's inverse proportion. Then we also talk about Charles' law, which says that the volume of a gas is directly proportional to its temperature. Then we have the general gas law, where you combine the Boyle's law and the Charles' law. So in the Charles' law, you have V is proportional to T over P. That's the volume is directly proportional to the temperature, but inversely proportional to the pressure. Now, next we have the ideal gas law, where we introduce two new constants. The product of the volume and the pressure is equal to the product of the number of moles, the universal gas constant, which is R, and then plus times the temperature of the gas in Kelvin. So that was the equation for the ideal gas law. And then today we are going to be extending that knowledge into more laws. Today we will continue from there, and we'll talk about Dalton's law of partial pressures, and we'll talk about Avogadro's law. So let's start from Dalton's law. Dalton's law basically says that whenever you have a mixture of gases that are not reacting chemically together, that means the pressure of one of those gases is equal to the partial pressure of that gas in the mixture. So basically, it means that the partial pressure of that gas, if you are looking for the pressure of the gas of the mixture, so it is the relative is dependent on the relative number of moles of the gas in terms of the total moles of the gases in that mixture. So in simple terms, what that means is that the total pressure of a mixture is equal to the sum of the partial pressures of the chemical substances or gases that compose that mixture. So the formula for finding the partial pressure, so that's P, the partial pressure P equals to the number of moles of the gas, the relative number of moles of the gas. That's, if you are looking for the partial pressure of the gas, it will be number of moles of A over the number of moles of A plus number of moles of B plus number of moles of C, and so on and so forth. It depends on how many gases you have. Then you multiply that by the total pressure. So that's P total. So this is the general formula. So let me zoom in so you can check it very well. So this is the total pressure. This is the formula. So you can probably see this clearly now. So the the partial pressure of a particular gas is equal to the number of moles of that particular gas divided by the sum of the number of moles of all the gases. That is how we got Dalton's partial pressure. So moving on, we have that was Dalton's partial pressure. Then this formula is used for any calculations in that aspect. Then we have Avogadro's law, and Avogadro's law simply states that equal volumes of all gases at the same temperature and pressure, they contain the same number of molecules. So what that means is that equal moles of all gases. So if you have 1 mole of oxygen, 1 mole of oxygen and 1 mole of hydrogen, so these equal moles of all gases at the same temperature and pressure. So imagine you are measuring this at STP. So I mentioned in our earlier videos, we talked about the fact that STP is the combined conditions of 0 degrees Celsius or 273 Kelvin and 760 millimeters of mercury. That is the condition of STP. So now, when you have 1 mole of oxygen at STP and 1 mole of hydrogen at STP, so basically at the same temperature and pressure. So STP is just a sample of that. So it can occur at any temperature and pressure, but as long as it is the same, then this contains the same number of molecules. So so in summary, Avogadro is telling us that equal volumes of all gases at the same temperature and pressure contain the same number of molecules. So one volume of oxygen and one volume of hydrogen, they contain the same number of molecules. So and that is like a relationship between Gleduzown's law, Avogadro's law, and all the rest laws that stand for stoichiometry. And this Avogadro's law is a very important law because it connects the molecules with the volume as long as the temperature and pressure are equal. So let me give an example from Avogadro's law. We have imagine you have if you ask how many particles, or I say how many atoms are in 4 gram of, let's say, of carbon. Yes, of carbon 12. So how many particles are in 4 grams of carbon 12? From Avogadro's law, we have its constant, which says that 1 mole of every substance, 1 mole of every substance, and by every substance it includes carbon. So 1 mole of carbon 12 contains 6.02 times 10 to the power of 23 times 10 to the power of 23 particles. And these particles could be atoms, could be molecules, or could be ions. Now, in this, they ask us how many atoms. So we'll replace the particles with atoms. 10 to the power of 23 atoms. So we'll say if 1 mole contains 6.02 times 10 to the power of 23 atoms, 1 mole is what? 1 mole is also equals to 1 mole of carbon 12 is 12 grams. So 12 grams is 6.02 times 10 to the power of 23 atoms. So and then we're looking for how many atoms will be in 4 grams. So 4 grams is equals to x. So let's make a direct proportion. 12 grams is equals to 6.02 times 10 to the power of 23 atoms. 4 grams is equals to x. So when you cross multiply, then and you divide them both sides by 12, you have x will be equals to 6.02 times 10 to the power of 23 times 4 over 12. So that gives us 4 in 4 1, 12 in 4 in 12, that's 30. So when we divide both sides, we have x will be 2.007 times 10 to the power of 23 3 atoms. So these are the type of calculations you'll be seeing in your examinations. So this is just a sample I've worked here. So let's move on to the next part of the video. So and from there we have from Avogadro's law we have the statement of molar volume, which says that molar volume is the volume occupied by 1 mole of any gas at SCP. So you know that Avogadro's law says that equal volume of all gases at the same temperature and pressure contain the same number of molecules. So that means if we take SCP for example, standard temperature and pressure, that means all gases at SCP will contain the same number of molecules. So if those gases have the same volumes, equal volume of all gases will contain the same number of molecules. So if we have 2 centimeter cube of oxygen and we have 2 centimeter cube of hydrogen at SCP. Now when we count the amount of molecules by different chemical means, we'll find out that the molecules in the two are the same at that temperature and pressure. So that means then we can also so we call that the molar volume. We is generally known as 22.4 dm3. So that's the volume of any gas at SCP is 22.4 dm3, and that molar volume is the volume of one molecule. One molecule of any gas at SCP is 22.4 dm3. So next, let's move on to Gram's law of diffusion. But before that, let's brush up on an example I talked about in previous video. First, let me give an example. If you have a question like this in your exam, this is also a under an empirical formula. So we have a hydrocarbon contains 20% of by mass of hydrogen and has a molar mass of 30 grams. Calculate the molecular formula of the compound. So in episode 4, I calculated the empirical formula of compound, but I didn't step it further. So basically, a hydrocarbon is a compound that contains of 2 elements, hydrogen and oxygen. So that being said, let's work this. So if carbon is 20%, and that means if carbon is 20%, I know that it consists of hydrogen and carbon. So that means hydrogen will be 80%. Right? Let me cross check that. Okay, sorry, 20% of hydrogen. So hydrogen is 20% and carbon is 80%. So let's divide both sides by their respective relative atomic masses. So for hydrogen we divide by 1 and for carbon we divide by 12. because the mass of carbon is 12. Now, when we divide 20 divided by 1 for hydrogen, we have 20. When we divide 80 divided by 12, we have 6.7. If we divide both sides by the smallest number, namely 6.7, 6.7, so about 6.7. So 6.7 will cancel 6.7. Then 20 divided by 6.7, that will give us 3. That's 3 ratio 1. Now is the simplest ratio, or the empirical formula ratio of the hydrogen and carbon in the hydrocarbon is 3 ratio 1. So that will be 3 atoms of hydrogen and 1 atom of carbon in the simplest ratio. So we are not done yet. We are looking for the molecular formula. Now the formula for calculating molecular formula is given by molecular formula MF is equals to N open bracket empirical formula EF. So what that means is that your molecular formula is gotten by multiplying your total mass in your empirical formula by the number, by that specific number. So there's a specific number we'll calculate here. So the molecular formula, we don't know it yet, but let's look for M. So now MF is 30, as stated. The question says it has a mass of 30. So let's say 30. The total mass of the molecular formula is 30, will be equals to N open bracket. The total mass of the empirical formula is, that's CH3. C is 12 plus H3. That's 3 atoms of 1 gram of hydrogen. That's 3. So that's 12 plus 3. That's 15. So when we divide both sides by 15, we are left with N is equals to 2. So that means when you multiply your atoms in your empirical formula by 2, you get a molecular formula. So that means molecular formula MF is equals to C. 1 multiply C by 2, that's 2C. Multiply 3 hydrogen by 2, that's 6 hydrogen. That's C2H6. That will be the molecular formula. And this particular compound is known as ethane. So that being said and done, let's move on to the next and the last part of this video. We'll talk about Graham's law of diffusion. And Graham's law of diffusion simply states that the rate of diffusion of any gas across a porous medium is inversely proportional to the mass of the gas. So basically what that means is that the rate R is proportional to 1 over root M. So, and I forgot to add, it's actually the root. So the rate of diffusion of a gas is inversely proportional to the square root of its mass. So that is, and that rate of diffusion of gas is also inversely proportional to the square root of its vapor density. And basically, the vapor density of a gas is simply the ratio of the ratio of the mass of a particular volume of the gas divided by the mass of the same volume of hydrogen. So that will, when we simplify the equations, we have vapor density is equals to half of the molecular mass. So these and more, these are the 2 major formulas you need to use to calculate Graham's law of diffusion, and it often comes out in chemistry objective questions. So in summary, we talked about gas laws, we talked about Gleduzown's law of combining volumes, which Gleduzown's law of combining volumes, which states that yes, if gases combine together, they do so in volumes which are equal in ratio to one another and to the volume of the product formed, if gaseous. So what that means is that the volume of that gases, the volume of the product form is proportional to the volume of the product and the volume of the initial gases. So and they are in simple ratios. Then we have Dalton's law. I talked about Avogadro's law, Avogadro's calculation. We talked about calculation and molar volume. We talked about Graham's law of diffusion, and then finally we talked about empirical, how to calculate your molecular formula from your empirical formula. So thank you for watching.